Moving on to some AP style questions here. So to start off, we have a ball attached to a string going around in a horizontal circle. And we want to know what would happen if we change the radius of the circle to 4 times as much, assuming the same force is applied. So this is one where we're going to set up our original situation and also our new situation. So in this case, we're thinking about the centripetal force being applied by the string, or our tension force. And we know that that stays the same. So I'm going to imagine this situation here where the ball's going around in a horizontal circle, and we have that inward force of tension, which ultimately leads to our inward acceleration. Now there's probably some vertical forces here as well, but I'm not really concerned with those in this situation. Based off of this, I'm going to set up my F equals ma, and the reason I'm doing that is I do know that this force stays the same, and so I need to get that centripetal force, which is tension in this case, into my equation here. So my original equation is going to be Ft equals m times my acceleration, which is v squared over r. Okay, that force of tension is the only force keeping it moving in a circle. My new equation, Ft stays the same. The mass of the object stays the same. My velocity changes, so I'm going to call this v prime squared, and my radius is now 4r. Simple way to combine these, I see that they're both equal to Ft, so I'm just going to go ahead and set them equal to each other. So I have m times v squared over r, we'll change it to a capital R because it does say that was my initial radius, equals m times v prime squared over 4r. I know that I can divide out those m's and I can divide out those r's, and so what I'm left with is v squared equals v prime squared over 4. I'm going to multiply both sides by 4, so I get 4v squared equals v prime squared. I can take the square root of both sides, and I find that my new velocity is 2 times my original. When I take that square root of 4v squared, I take the square root of both the 4 and the v squared. And so I have an answer here of d, twice the original speed. Moving on to question 10, we have a situation where we have a coin on top of a turntable, on top of a record, rotating around. And we want to know which of the following directions best represents the direction of the frictional force on the coin when it is in the position shown. So we should know right off the bat that while it's going around in a circle, it has an inward acceleration, so at that point it is accelerating downward. If we think about this coin as it travels in a circle, there's really only one force that can exist to cause that inward acceleration. Okay, we need some force inward to create this acceleration. The only force that we really have that could do that is friction. And so that force of friction is that inward force. So when we're at that top point, that force of friction is just down, making the answer C. So we have another experimental design one shown. So we have this device that's shown in the picture here where there is a string going through a glass tube, and it's attached to a ball that goes around in a circle on the end here. We have a spring scale attached to the cord, okay, and we're swinging the ball around with a known radius of r. And so what we want to do is we want to derive a procedure that would allow us to determine the mass of the ball based off of this setup. So what I'm going to do is I'm going to skip right here to part 4 of this. I'm actually going to answer that part first because that's the how would you actually get this part, and I think that's going to make it easier to answer parts 1 through 3. So to start thinking about 4 here, I'm going to think about the forces acting on the object. I'm going to go ahead and draw those forces. So the force we're going to have, we have the force of tension acting on the ball, of course. That's the force keeping it moving in a circle. This is once again the side view here. I'm also going to have a force of gravity going down. So that's all the forces I really have for now. Now there is this line here about assume the string is horizontal. We'll come back to this idea because you're probably thinking, well, why isn't this object accelerating down? That is something we'll address in a second. But for now, we really actually only care about this force of tension anyway because that's the force keeping it moving in a circle. So we can go ahead and set up our F equals ma, so our force is in the x equal max. The only force we have causing that inward acceleration is that force of tension. So that's equal to the mass times v squared over r. So ultimately we're looking for the mass here, so I'm going to go ahead and rearrange this equation to solve for that. So I'm going to multiply both sides by my radius r and divide by v squared, and so my mass is going to be ft times r over v squared. Now let's think about the things that we know. We're told that the radius is known here, so we don't have to worry about finding that. And the tension we can get from the spring scale, okay, so we don't have to worry about that part either. However, we do need to figure out how we're going to determine this velocity. So we know we have a stopwatch, and we do have a way of finding the velocity of an object moving in a circle, and that is 2 pi r over t. Once again, we know the radius here, so we can time the period, okay? And we can substitute that in. So we should write a few words here to supplement this procedure. So the first thing I would say we're going to do is we're going to use our measured period, use this time that we're going to measure with our stopwatch to solve for our velocity. And I'll go ahead and cite that equation. Then we're going to take that over here and use this equation to ultimately solve for mass. There we have it. And the one thing we maybe add in parentheses is just acknowledging that radius is known. We were told that, so that's not something we need to calculate, but it's probably a good idea to mention that. So there's part 4. There's what we ultimately need to do. So we see the two things we need to get data on are the force of tension and the period. So that's going to help us go ahead and do parts 1 through 3. So let's go ahead and do that now. Now that we have that, what quantities would be measured? It would be the force of tension in the string and also the time for one revolution, or the period. Next asks us what equipment we would use and how that equipment would be used. For this one, it's not that difficult because we're told exactly what equipment we have, but we should still mention what that equipment is and include this brief label diagram of the setup. So there we have it, a statement of the two pieces of equipment, the spring scale for tension and the stopwatch for the period. And then I'm going to include a brief diagram here. We kind of have one given, but we should include one anyway. So there we have a very basic diagram showing the mass attached to the string with the spring scale attached to that, and then the stopwatch on the side. And so that's really all we need for that. For the last part, describe this experimental procedure. First of all, we always want to state what we would actually do to complete a trial. So we're going to swing the ball in a circle at a constant speed. Next, I would say we're going to measure the time for one period and record the force while we're spinning it at this constant speed. The last thing I would say, and this really relates to this line here, explain how to reduce experimental error, is that we would repeat this several times, and ideally we would swing it at various constant speeds. Each time we are going to swing it at a constant speed, but changing that constant speed is only going to help our readings and shouldn't affect the mass of the object, obviously. So there's part A. I'm going to go ahead and erase this and move on to part B. So for part B, the first thing we're actually asked to do is draw the forces acting on the ball. So I'm going to take my free body diagram that I had drawn earlier and use that there. So that's what the forces acting on the ball would look like. We already had done that. And now we want to explain why it's not possible for the string to be perfectly horizontal. And that's where we come back to this idea that we have gravity acting down on this object, but as you can see, nothing to balance the force of gravity. So the reason why it can't possibly be completely horizontal is we need some force going up to balance the force of gravity. And where do we get that force from? Well, if our tension is up at an angle, then we're going to have components of tension, and that vertical component of tension can balance the force of gravity. So to explain this, I'm going to start by just stating that the force of gravity is acting down on the object. And then I'm going to say that there must be a force to balance that downward force of gravity since the object is not accelerating vertically. And then the last thing to kind of really tie this all together is if the string is at an angle, the y component of tension can provide that force. But if it's completely horizontal, there is no y component of tension. And I'm just going to wrap it up by saying, therefore, the string must be angled, bringing all of this together to really get back at the ultimate question of why the string cannot be perfectly horizontal. Okay, so we're moving on to the next problem here. So we have a situation with two cars going around this track here. And we're told that both cars go around these curves, which have a length of d, at a constant speed of vc. Car X, once it goes around the curve, is going to speed up for half the straightaway to a speed of 2v, and then slow down for the second half back to a speed of v to go around the curve at a constant speed. Y, on the other hand, is going to speed up over a quarter of the straightaway, so from here to here, to a speed of 2v, maintain that speed of 2v, all right, for half the straightaway, and then slow down for the final quarter back to v to go around the curve. All right, and so we have a few questions starting with simply identifying the direction of the net force, which is going to be the direction of the acceleration of each car as they go around the track. So let's start with car X, keeping in mind that it's going around counterclockwise. So I'm going to start with this point here. Around that curve, we know it must be accelerating inward at that point. It then gets to the straightaway, and it's going to speed up for the beginning part of the straightaway for the first half. Okay, reaches the halfway point here, and then when we get to this point here, we know that it's going to be slowing down because it slows down during the second half of the straightaway. We continue on around to get to the curve section of the track. Once again, at that point, we're going to be accelerating inwards towards the center of the circle. We then reach this dot here where we're going to be speeding up once again. So our acceleration is in the direction of our velocity. And then we get to this point here where we're going to be slowing down. So our acceleration is opposite the direction of our velocity. Moving on to car Y, the curve sections here and here are going to be identical because the motion of car Y is identical at those two locations. Okay. Let's take a look at some of the other ones. So once we go around that curve part, we speed up for a quarter of the straightaway. So this is definitely in that quarter of the straightaway where we're speeding up. We then maintain a constant speed through that middle half of the straightaway, and then we're going to slow down in the last quarter, so that last dot is going to have an acceleration opposite the velocity. We then continue on around the curve, get to this point. Once again, we're speeding up initially. So we're going to draw an acceleration vector in the direction of our velocity. Then we hit that constant section, so that very last dot there is going to be an acceleration of 0 because that's when we're traveling at a constant speed. Part B asks us to state which one completes one trip around the track in less time, and we want to go ahead and justify that without using equations. This one's actually a little bit of a throwback to some kinematics things, but that's good review anyway. So, which one completes the trip in less time? Well, we note that car X increases to a maximum speed of 2v right at the middle of the track, okay, and then slows down for the remainder of the time. However, car Y hits that speed of 2v, all right, after going for only 1/4 of the straight section, and then it maintains that for half of it. So it's traveling at a speed of 2v for much longer than car X. Okay, the curves are identical for both. All right, both go around the curve at a constant speed of vc. All right, so the curves aren't going to be any different, but for the straightaways, car Y is going to travel faster. And my justification for that, a few points I'm going to make. Number one, their motion is identical around the curves. Second point I would make would be that Y accelerates faster and maintains a speed of 2v for a longer period of time on the straightaway. And then just bringing it all together, therefore car Y goes around faster. So there is our conceptual explanation of this. Let's go ahead and do a mathematical one. For part 2 of B, we want to justify this quantitatively with appropriate equations. So I'm going to break this into a curves section and a straightaway. So because we're traveling at a constant speed on the curve, I can use the equation speed or average speed equals distance over time, since that speed's not changing. So our speed along the curves is just going to be VC, our distance is going to be D, and we can solve for our time. So going way back to the beginning of the year, we have speed as distance over time. So VC is D over T, which means the time for one curve is going to be D over VC, which means that two curves, since we're going around the track one time, is going to be 2D over VC. So there's my time on a curve. For the straightaway, there's really two parts to it for car X at least. We're speeding up for half. So our displacement is D over 2, and we're going from a speed of VC to 2VC. Okay, we don't know our acceleration, so I'm just going to leave that blank, and we're solving for our time. So I'm going to use the equation 1/2 VF plus VI times T. So I'm going to say D over 2 is equal to 1/2 times VC plus 2VC times T. So D over 2 is equal to 1/2 times 3VC over T. I can go ahead and solve for time. The two 2's on the bottom there cancel out. I divide by 3VC, and I get the distance over 3VC equals the time to speed up. Now, we could go and solve for the time to slow down, or we could realize that it's symmetrical. We're going from V to 2V over a distance of D over 2. If we flip that around, we'd really just be changing which one's the initial, which one's our final, but it would work out the same. Okay, so that D over 3VC is the time to speed up. It's also the time to slow down. Okay, so our slowing down time is also going to be D over 3VC, all right, which means one straightaway is going to be 2D over 3VC, and there are two straightaways total, so that means that our total time for the straightaways is going to be 4D over 3VC. So our total time for X is going to be the time for the two curves, which is 2D over VC, plus the time for the two straightaways, which is 4D over 3VC. I'm going to multiply this one by 3 over 3, so I end up getting 6D over 3VC plus 4D over 3VC. And when I add those together, I get my total time for X is 10D over 3VC. I'm now going to think about car Y here for a second, and this should be a little bit quicker actually. So for the curves, the total time for car Y is going to be identical to car X. So our time is just going to be 2D over VC, and that's the total time. In both cases, they travel around those curves at a constant speed, so that's not going to change. My straightaway time will change, okay, and for car Y, it's actually going to be a little bit more complicated because we are speeding up, traveling at a constant speed, and then slowing down. So let's break that up into those three parts. So for the speeding up portion, we speed up over a distance of D over 4. We go from VC to 2VC. So we're going to set up the same equation that we did for car X, the 1/2 VF plus VI times T. And so we can say D over 4 equals 1/2 VC plus 2VC times T. I'm going to multiply both sides by 2 and combine the VC's, so we end up getting D over 2 equals 3VC times T, which means that our time for speeding up is going to be D over 6VC. That also is going to be our time for slowing down. Just like in our original one, we speed up and slow down over the same distance. The only thing that's flipped is which is the initial velocity, which is the final. So that means our time for slowing down is also going to be d over 6 vc. Okay, and then our time going at a constant, we're going to have a distance there, and I'm just going to use speed equals distance over time. We're going to have a distance of d over 2, an average speed for that portion of 2 vc, and we can solve for our time. So we can say speed is distance over time, average speed that is. So 2 vc equals d over 2 all over t. So that means that our time for that half section of track when we're traveling at a constant speed is going to be d over 4 vc. So combining all of these times, the time for one straightaway for car Y is going to be d over 6 vc plus d over 6 vc plus d over 4 vc, and that's going to be equal to, making all of these 12 vc, we get 7d over 12 vc. So just finding that common denominator here. So that's the time for one straightaway. So we're going to multiply that by 2 to get the total time for both straightaways, so 14d over 12 vc. If we combine that with our total time for the curves, all right, putting those two times together, I know we're getting a little messy here. We have 2d over vc plus 14d over 12 vc. I'm going to multiply top and bottom of this fraction by 12 to get a common denominator there. So we end up with 24d plus 14d over 12 vc, which ends up being 38d over 12 vc, which we can simplify to 19d over 6 vc. All right. If we compare these two times, 10d over 3 vc and 19d over 6 vc, we find that this is a smaller time, not by much, but it is a little bit smaller. If we had made this over 6 vc, it would have been 20d over 6 vc, so more time than this one. So for this last part here, we want to explain how our equations in B So for part C, we want to discuss how our equations in part 2 of B justify or explain what we said conceptually in part 1. We don't want to just go right to the final answer and say, oh, well, it was less time. We want to really focus on what we said in part 1 and how that relates to the equations in part 2. So I would say for this one, we see that car Y accelerates to its top speed of 2 vc in a time of d over 6 vc. But car X, on the other hand, takes a time of d over 3 vc. So Y gets to its top speed faster, okay, and then it stays at that top speed for a period of time that X does not. And then I think you could even say that overall, car Y takes a time of 7d over 12 vc on the straight part, whereas car X is going to take a time of 2d over 3 vc. And I know this might sound like a minute detail here, but this really is what you want to do if you get a question like this, because we don't want to just jump to the final answer of, oh, this one's 10d over 3 vc and this one's 19d over 6 vc. We mentioned specifically how car Y speeds up faster and maintains that speed for a longer period of time. And so we want to focus on the time it takes for each one to speed up. That's really the key here.